Okay, hello, welcome back. So in the previous video, we saw the Hamilton's canonical equations, and that corresponded to the condition that the system was unconstrained, and that is all the generalized coordinates were independent, and the system was only consisted of holonomic constraints like pins and sliders and so on. Here we'll see how we can include other conditions. For instance, if we have closed kinematic chains or other non-holonomic constraints into the Hamilton's equation, and we'll see another form of writing Hamilton equation in matrix form that could be easy, could make things easier. So to begin, let's see. So for the canonical form, the unconstrained, let's write it this way: independent Q's and holonomic system. Holonomic system for this condition. That's a system. And the Lagrange equation where d over dt of partial L partial q dot I minus partial L partial qi equals 0. And corresponding for this condition, the Hamilton's equation, and let's put a comma. We had q dot I was partial h partial pi, and p dot I was minus partial h partial qi. So this was the canonical form. Now if, let's put a dot, if, what do I have next? If we have conservative forces, so the Lagrange form e over dt partial L partial q dot I minus partial L partial qi was equal to these q primes, the generalized non-conservative forces. So similarly, the Hamiltonians, q dot I, these ones remain unchanged. But the p dot I, which is gonna be the more important one, although they're equally important. Go. P dot I is same derivative, qi, but now plus same q prime I. And we also saw if q, let's put it this way: if we have constraints, so not all q's are independent or non-holonomic. So in this case, the Lagrange equations were like this: partial L partial q dot I partial L partial qi. Oh, that's nice. qi was q prime I plus some lambda summation lambda down ji. No, wait, lambda j a j I, j from 1 to m. We had m constraints, and these lambda j's were the Lagrange multipliers, tightly related to the idea of the constraint forces. So in this case, the Hamiltonians, again, q dot I remains the same, partial h partial P dot OPI. This is partial PI and Q dot I, P dot I is minus partial H partial QI plus Q prime I. Again, same form. Sum of lambda J A J I J from 1 to M. And now in this case, we have Q dots, P dots, and lambdas as unknowns. So we need another set of equation, and those are the, let's call it F. The, what is this? Go. The F, the constraints were sum over Fj. We have M of those. I from 1 to N, 1 to N of AJ I Q dot J Q dot I. Yes, because the summation is over I. J I Q dot I plus A J T equals 0. And we have M of these equations. And 2n of those equations we solve for all the Q dots, P dots, and lambdas. And this is valid, this equation is valid and needed. Either we are working with Lagrange or Hamilton set of equations. And another thing I wanted to discuss or mention is specifically for these scleronomic systems, those that T time does not show up in equations. So for those particular systems, remember we can write kinetic energy as 1/2 summation I equals 1. My laptop is sad again. Go. Summation I from 1 to N, summation J from 1 to N, Mij, Q dot I, Q dot J. So you can write this in a very nice compact form using matrices. So Q dot transpose. So this is, so when I use this Q, it means it's a column vector of Q1, Q2, and so on. And the transpose version is, it becomes a row matrix. M matrix, which is all these Mij's. Q dot, and I have 1/2 here. So if you have this, let me write it as T equals. So in this very nice form using vectors Q or column matrices Q's and the mass matrix M. If we write it this way, then P, the vector containing all these momentas, is going to be M. If you take derivative, MQ dot. And from here, if you need to find q dots, because later you want to write kinetic energies or other Hamilton's stuff in terms of P's and Q's, you have to find Q dots in terms of P's. So what you can do is multiply both sides by inverse of M. So Q dot becomes M inverse, the inverse of mass matrix, times P. And finally, for these systems, we just saw that the Hamiltonian is the total energy, mechanical energy of the system, so T plus V. I wrote one line, and it takes forever to show up. And in this case, so if you write Q dot as M inverse P and plug this up there, in definition of T, so it's going to be 1/2 P transpose M inverse P, and wait for it to show up. Good. Oh, I wrote other stuff, didn't show up. Times P. So this is the kinetic energy written as a function of momentas, or in terms of momentas, plus V. And V is itself function of Q. So, don't do that. Go back. Functions of Q's. So this is a very easy way to find the Hamiltonian for good systems. Good systems means those that do not have these internal changes with time. And all you need to do is to find mass matrix. There are different ways you can do that, and you can write Hamiltonian fairly fast using these matrix multiplications. All right, that was all I have for now. I'm debating whether I need to include another video on Hamilton or skip it. So let's see what I think. I'll see you soon.